Hey students, in this video we're going to talk about similar triangle postulates. So before we get started, I'll have you assess yourself on the learning target for today. We're going to be determining if triangles are similar using the similarity postulates. So to get started, I want to ask, what does it mean for two triangles to be similar to each other? I have this little cartoon that I found here, and take notice that the two triangles say that they are similar, and it has some of their sides labeled here too. Take note of the 15, this is a 21 if you can't see it, a 5 and a 7. What are some of your thoughts on what it means for triangles to be similar to each other? So we have this sort of left-hand side of each of the triangles, and as I said before, the larger one is 15 and the smaller one is 5. Then we also have sort of the bottom side. It says 21 there, I'll put it here so we see it nice and big, and also a 7. And if you notice, the blue triangle on the left is actually 3 times as big as the pink one on the right. If I multiply 5 times 3, that gives me 15. And if I multiply 7 times 3, that gives me 21. So sort of an informal definition of similar triangles that I typically tell students is that triangles are the same shape, but they may be proportionally different in size. And so these two triangles have a very similar shape to each other, meaning that their angles are actually the same, but they are proportionally different in size. Particularly, they're proportionally different by a factor of 3. And it's important to note that they multiply by some sort of common factor, or they could divide by a common factor, like technically dividing the blue triangle sides by 3 would give us the pink triangle sides if we go the other direction. But they can't add or subtract by a common factor. They need to multiply or divide. So with that definition in mind, I'll ask you about these two triangles here. We have triangle ACB and triangle QRP. Are these triangles similar? What do you think? So if you notice, they have sort of related angles. They have this 27-degree angle A there, and they also have a 27-degree angle in the other triangle. Same with 45 and 45. Now, the thing about triangles is that all the angles of a triangle should add up to 180 degrees. So if I were to do the calculation of adding 27 and 45 and subtracting that from 180, that'll give me some numerical value for angle C. And since these two angles are the same as the ones on the left, angle R should also be the same size as angle C. And so that means all 3 angles of each of the 2 triangles are the same, at least the ones that they correspond to, and so that means that the 2 triangles are similar. But to make things a little bit easier for ourselves, we don't have to actually know that all 3 angles of a triangle are the same to prove that they're similar to each other. We actually only need to know that 2 of them are, because if we know that these 2 corresponding angles are the same, then we can conclude that the third one should be the same too. And this is called the angle-angle postulate. 2 triangles are similar if they have 2 corresponding angles that are equal in size. So let's use that postulate to practice this example here. The question is, which triangle is similar to PQR? So I have triangle PQR right here. And the question is whether triangle STU or triangle ABC is similar to that one. And I'll let you take a moment to think about that. In the meantime, I'll take notice that these angles up here are matching to be 100. And But this third angle, angle P, which is 45, doesn't quite match up with the other ones. It's obviously not 35 and it's obviously not the same as 55, but it could match up with these blank angles that we have here. So maybe we can use a little bit of addition and subtraction to figure out which of these is supposed to match up with angle P. And another way to think about that is we could solve for angle R, for example. So 100 plus 45 would give me 145. And if I subtract that from what all the angles should add up to in a triangle, which is 180, that's going to give me 35. And so that means that this triangle is similar to triangle PQR. And while we're at it, I'll go ahead and write that similarity statement here. So we have triangle PQR, and we use the little squiggle line to show that two triangles are similar. We don't say equal because they're not equal in size, they're similar to each other. And that is similar to triangle STU. So there's also a way to tell if two triangles are similar by looking at their side lengths. We looked at that first example previously that we were able to find a common factor that all of the sides could multiply to get to the other one. In this example, it looks like I could multiply 4 times 3 again to get 12. That works for this other side length as well. And 7 times 3 equals 21. But we also can set up what we call proportional ratios. And how that's going to look is we're going to set up two fractions that would be equal to each other. And I'll explain more in our next video why being able to set up these proportional ratios is really helpful to solve for missing sides. But for this video, I just want to show you kind of the relationship. So for example, we have this side, this green side as I labeled it, that has a length of 4 and this green side of 12. And then I also have the blue sides on the bottom, 7 and 21. If I were to write a ratio of some of these sides, for example, if I were to write a ratio of 4 over 7, if these two triangles are proportional to each other, that actually should be equal to the corresponding sides of the larger triangle, 12 over 21. And we can use a calculator to verify that. If I do 4 divided by 7 in a calculator, I get 0.5714 and some other numbers repeated. And if I do 12 divided by 21, also in a calculator, I'm going to get that same value of 0.5714. And that tells me that these two triangles could be similar to each other. And there's actually many other ways that we can set up proportions to prove that these triangles are similar to each other. An easier way to have done it is if I took the large green side and divided that by the smaller green side. So if I did 12 over 4, that also should be equal to if I do the large blue side over the small blue side. As long as you set up corresponding sides with each other that match with both triangles, the proportions will work out. And so we have 12 over 4 is equal to 3, and 21 divided by 7 is also equal to 3. And so that also shows that those two triangles are similar to each other. And if I got different values for this, then they would not be similar. So it turns out there are several similarity postulates that are going to work with determining if triangles are similar or not. we already talked about the angle-angle postulate. If we know that two angles are the same in each of the triangles, then they are similar to each other. The second one is the side-side-side postulate. So if we have three sides that are proportional, then by setting up those ratios or just determining a common factor that we could multiply to get from one triangle to the other, then those triangles are similar to each other. And I could have set up a third ratio, but I have this side over here, 12/4, that is the exact same as the green sides. And then there turns out to be a third postulate that also allows us to determine if two triangles are similar to each other. And that's if you have two angles that are the same, and also if you have two sides on either side of that angle that are proportional to each other, that you can set a proportional ratio and determine that they're equal. Okay, so let's do a little practice here. The question is, are these triangles similar to each other? And so I'm kind of taking a look at them and noticing that we have this 50-degree angle here. And I noticed that there's kind of like a reflected 50-degree angle, sort of reflected and rotated a little bit in this other triangle. So what could be going on here is I have side AB could be similar to side FD, and also CB could be similar to side FE. And so I'm going to set up a ratio to see if those are similar to each other. And so let's just kind of take what we see here. We have the first ratio that you set up really can be anything that you want it to be, and then you'll just match the other ratio with the corresponding sides with the first one that you set up. So let's try 12/24. Let's do that. That seems like it's going to be an easy enough fraction since 12/24 is just 1/2. And I'm going to see if that's going to equal the corresponding sides of the other triangle. Since I have 12 on top and 24 on bottom, I'm going to need to have the green side on top and the blue side on bottom of the smaller triangle as well, which is going to be 8/16. And 8/16 is going to be 0.5, and so is 12/24. And so that checks out. These two triangles are similar to each other because they have those corresponding sides that work out in the ratio, and they also have this angle with the 50 degrees there that determines if they are similar or not. Okay, so kind of a follow-up question is, why are the triangles similar? And to tell why triangles are similar, you want to pick one of the postulates, one of the similarity postulates that I spoke about in the previous slides. Is it because of angle-angle postulate? Is it because of side-side postulate? Or is it because of the side-angle-side postulate? And you can determine this by seeing that there is an angle involved and two sides in each of the triangle. And so that means it's going to be the two triangles are similar by the side-angle-side postulate. Okay, and that's it for the lesson today. Before you go, I'll have you assess yourself on the learning target. We determined if triangles were similar using various similarity postulates, and that'll be it for the lesson today.